Hello everyone. So we will be starting very soon with the presentation. First of all, I would like to thank you everyone. Thanks everyone for attending today's webinar, which is organized by the SFP UK chapter. As you may already know, the SFP is an international professional society representing those practicing in the field of fire protection engineering. The primary mission of the UK chapter is to support and represent its members and those interested in fire protection engineering. One of the main ways of doing this is to provide continual professional development and other training events. Today, I, Konstantinos Kotzoglou, an associate from OFR Consultants in the UK and responsible for online seminars at SFP UK chapter, I'm more than happy and pleased to organize today's webinar titled Data Centers, Fire Engineering in an Evolving Sector. I'm very happy to host Jonas Fuchs and Joshua Parker from Joule Group, who will be presenting and providing us insights regarding the design of data centers and key fire safety challenges for such. So, guys, first of all, thank you for joining and also taking the time to prepare this presentation for us.
For the invitation.
Thank you. Thank you for the introduction.
So just before we start with the presentation, all microphones and cameras are disabled. So please write down any questions for Jonas and Joshua on the Q&A section, which we'll be using right after the presentation. We will try to address as many as possible after the presentation. And also just to make a note here that we will be recording this presentation and will be made available through the SFP UK chapter website at a later stage. Now, before we start, of course, a little more information about our presenters today, who will be Jonas and Joshua. So I will start with Jonas. He's a fire engineer working with Joule Group since 2020. He is a chartered engineer with background in construction compliance, passive fire protection, and first principles fire engineering. He is a graduate of fire engineering degree from Edinburgh University, and before joining Joule Group, worked with several other companies, Arum, Mott MacDonald, and Hollea. Some of the past projects include critical infrastructure developments for major railway developments, healthcare, aviation, complex high-rise projects, and industrial and power generation developments. Jonas has been involved in data centers projects since 2017 across the UK, Middle East, and Europe, contributing to over 20 data center projects and sites. On the other hand, Joshua, our second presenter for today, has worked as a fire engineer since 2017. His main experience comes in the form of development of fire compliant designs for multitude of projects across varying sectors. He's a graduate with a fire engineering degree from the University of Central Lancashire in 2017, before starting his career at Omega Fire and later at BB7. More recently, he joined Joule Group in 2022. Joshua's projects highlights include sectors ranging from high-rise residential to aviation, test facilities, and convention centers. As of 2022, Joshua has been engaged on several significant data center projects located throughout the UK and Europe, assisting in the delivery of more than 15 such sites, inclusive of new build and retrospective designs. Guys, thank you so much for attending today. The floor is yours, and so we will be starting with the presentation now. Just a note, all questions to Q&A, I must repeat that, please, so we can have it later on.
Thank you very much for the introduction, Konstantinos. As obviously you've just gone through our introductions, a little bit of housekeeping before we obviously proceed with today's presentation. The session is going to be recorded. we will be sharing all slides at the end of this presentation in PDF format. Obviously, if you do want to have your own personal copy, please reach out. Our contact details are available at the end of this presentation as well. It is solely an introduction into the key design challenges, risks, and areas to look out for on data centers, and shouldn't be seen as design advice. Obviously, every project, no matter if it's a data center or elsewhere in our sector as fire engineers or the fire related disciplines, each project has its own special and unique circumstance, and also this presentation shouldn't be sort of applied across the board to data centers as a whole. As leaning into that, it isn't a training session. It is just an introductory session into data centers. If you could go on to the next slide, please, Jonas. So Dual Group, we are a fairly new company within the fire engineering sector, but despite being new, we do have a good level and wide-ranging level of experience throughout the company. We currently have over 30 fire engineers, and as noted there, an overall total of 290 years plus combined industry experience. We have several chartered engineers currently working under the umbrella of Dual Group, and we specialise in sort of more afield projects like data centres, critical infrastructure, aviation, as I think Konstantinos noted within Jonas's previous project experience. But we also work on the typical projects that we see as fire engineers day to day, including your residential and commercial schemes. We have offices throughout the UK, Ireland, and the Middle East. Originally being founded in the Middle East before returning home to Ireland, and then expanded into the United Kingdom about 5 years ago. We've delivered over 800 projects, with that continuing to expand across 20 countries. A number of those are data center projects, not just obviously to the UK, but throughout Europe. And it is probably worth noting that today's presentation is solely based on the UK regulatory position on data centers and advice relating to that. It doesn't lead into European designs or further afield, such as the Americas or Asian areas of operations. So next slide, please, Jonas. So as part of this presentation, we're just going to try and really break down the sort of the way in which we try to assess data centers, and it's very much sort of similar to how we assess other building types. First, we're going to look into how and what is a data center, what comprises of a data center, and then what applicable legislation applies to data centers, the criticality and importance of that legislation, how it impacts fire design, and how to identify and mitigate an appropriate response to those to any challenges, specifically fire challenges within the design of data centers. Next slide, please, Jonas. So what is a data center? It's essentially a big box, a facility that contains servers for the storage of data, but which performs the network tasks and acts as an intrinsic link to users and the obviously commercial aspect of how data traffic impacts each and every one of our lives every day. It's often or more often than not becoming a critical building in the sense of AI powered facilities, cloud services such as Microsoft OneDrive and whatnot, AWS, etc., and they effectively act as the hub, the storage facility for that data, in order for us all to access that throughout our everyday lives. Often these buildings have incredibly detailed systems to support that facility, including backup power supply, generation, and cooling to also maintain the often in very large quantities of power consumption that is required of these facilities. And also the criticality to maintain that connection to data for users is an incredibly important component. So the considerations to those systems are quite considerable. As noted there, there's a continuous uninterruptible operation that is required of data centres, mainly due to the fact that they are now regarded by the UK government as critical national infrastructure. They're as seen as important as power generation sites, military sites, etc. They are are becoming incredibly key to the way in which our lives run day to day. Next slide, please, Jonas. So if we break it down into what the basic anatomy of a data center is, as I noted there, effectively a big shed, almost warehouse-like, and that's typically where you will see the storage of, or the location of your data halls, offices, and support areas. As part of the internal arrangement of that as well, you'll often find a breakdown for in terms of support areas, storage facilities, build areas for tenants to build the server racks, put them together, and move them into the data halls prior to operation and commissioning. And on top of that, obviously the support areas for offices, the connection between where the data is stored and how that data then moves out of the data center to the consumer, and likewise the data from basically the backward chain of that sort of data path. Outside of the data center, in order to support it, as we just mentioned on the previous slide, you often tend to find gantries or yards. These are often split between mechanical and electrical systems, backup generators, UPS systems, and cooling facilities. On top of that, you have obviously the presence of transformers and alike. But in the UK, we typically do see the use of a gantry structure as opposed to yards, just due to spatial constraints and planning requirements. We ultimately don't have the space in the UK to have extensive mechanical electrical yards adjacent to these buildings, and often they are on brownfield sites as well, so they're already constricted by existing structures around them. So putting these facilities on gantries is often the best means or the best means to use the space available to the data center to maximize the overall footprint of the actual data halls and the internal areas themselves. So next slide, please, Jonas. So breaking down what a gantry and a yard actually is, as I just mentioned there, they contain the mechanical and electrical systems. In the UK, we often do find the gantries contain all those systems, and that is brought down on often a multi-tiered sort of approach. So as noted there, you'll often have on the figures on your screen, you'll often have generators on one level, UPS battery systems, uninterruptible power supply battery systems on the next level, transformers and other associated systems on a third level. Obviously, that isn't limited to the number of levels of a gantry. That can change between each site and the power demands necessary by the operator. You know, what is the peak IT load of the data center and the secondary power and the energy storage systems that go with it. Are also dictated to by that peak IT load. More often than not, the gantry structures are separate to the main building structure, being fully independent and not actually part of the wider building structure itself of the data hall, which obviously leans quite well into the use of specific areas of guidance. But overall, the general arrangements are it's a stacked multi-story arrangement, basically such that all systems can be located in one area, one elevation, often of the building, and each deck has its respective requirements. A yard effectively has the same system, same items, but it's just spread out over a greater area of separation. Obviously, the lack of separation with gantries does present its own challenges, which we'll go further into later in this presentation. But generally speaking, in the UK, the gantry is the most common approach. Internally, we often find, I think that the figure's probably the easiest way to explain this, but the pink areas are what you typically see as the data halls. That's where the server racks are, and obviously inside of the data halls you have links to elements such as hot aisles, cold aisles, be that being the hot air, the air that is ejected from the server racks, and the cold air, the intake to those server racks to keep the systems cool. That is fed via the blue areas, which are the cooling corridors, and basically effectively the data a data hall acts as its own ecosystem, providing cooling to the critical systems within the data hall. We're looking to protect that data storage facility, and the biggest consideration for that is the cooling aspect. Around that, you obviously have the green areas, which are the circulation routes and corridors. Often you can find large travel distances for these within these circulation routes and corridors, connecting multiple areas of the data center just by virtue of the footprint of the building. And often accessed off those circulation routes are the storage areas and build areas. Store areas often are extensive and associated with tenants. So with a tenant, you may have the landlord or the operator of that data center who then rent out a data hall space to a subtenant, and they will have attributed storage areas, build areas associated with that data hall. And on top of that, you have the office areas, which obviously, as mentioned previously, is the interface between the outside world and the data stored within. And it's used for operations by basically the operator to maintain all systems, monitor all systems, traffic, power generation, secondary power backup. Everything goes through that office facility. An important part of data centers is obviously the loading bay. It's often we see that they are a sort of a continually expanding building. Often you'll find only a single data hall is fitted out at a time. Hence the need to expand into further data halls in the building and bring those IT components into the building via loading bays and acted as intermediate storage / staging areas before the items are then decanted to the formal storage areas in the building are typically crucial and sort of well considered spaces within these facilities. Next page, please, Jonas. So how does current regulation and guidance see data centers? The answer to that question is it doesn't really see it at all. Typically under the building regulations, a data center falls under a Class B building for general industrial use and storage and distribution, often more leaning towards the storage and distribution side of that scale. Obviously, that leaves quite an open gap in how you necessarily apply guidance and what are the applicable pieces of guidance to achieve compliance. Ultimately, we don't design data centers as storage facilities. They are quite a bit more than that, given typically the property protection requirements. Obviously, that isn't picked up within the building regulations, but there isn't any specific allocation towards data centers within the building regulations or supporting frameworks. So when we look towards guidance to support the building regulations applicability of the building, we look to approved document B first in terms of its purpose groups, but this can be quite restrictive in terms of how we apply the approved documents to data centers. Ultimately, the approved documents, as many of us know, are only really there for common building types, and a data center does sort of push the bounds of what a common building type is, having not been referenced within the regulatory guidance or the regulatory position. It would be fair to assess and assume that these buildings don't fall under a common building type. So we often find that the most appropriate and best fitting solution is to move down a BS 9999 route through the adoption of the risk profiles, as this allows a more tailored and specific set of outcomes and variables in order to tailor the fire safety design of that building to a more suitable position. Often we find risk profiles range from A1 to 3, but that can obviously be dependent on the various other systems within the building, be that automatic detection or suppression systems, all obviously have a bearing on what outcome or what risk profile we like to apply to that. But more often than not, the application of BS 9999 does provide the most flexible route to fire safety compliance. So when we look to adopt appropriate guidance, we, as we mentioned previously there, they shouldn't be designed as warehouses. So applying guidance for those particular buildings, you really shouldn't necessarily be adopted. We need to look more into provide more of a granular assessment to the, so the risks, the prevailing risks within that building. and what those risks present. How can we best overcome those risks, and what guidance would allow us to do that? The suitability of guidance should be considered owing to the complex nature of these buildings. So obviously leaning more towards a risk-based approach as presented in 9999 does enable that sort of application of guidance in these sort of best practice sort of means. But often what we find is the operators of these data centers do look to use or seek for us as fire engineers to use alternative guidance just by virtue of where the operators are often from, which does see the adoption more often than not of the NFPA suite of documents and the IBC to support any PS9999 design. Obviously, using the NFPA and IBC isn't a means to demonstrate compliance with the building regulations. We still rely on 9999 for that, but it helps to supplement specific systems that may be adopted within that building. But above all, good fire engineering practice should be adopted. If a lack of guidance exists, there will be an answer somewhere, and it's finding that answer through either the NFPA suite of information or the IBC or elsewhere within the British Standard suite of documents as well to find the most appropriate and tailored solution to the prevailing risk. So how do we apply your current guidance? As we mentioned, current guidance is not tailored to data centers, but when we break down the constituent components which form a data center, when we look at that particular risk associated with those particular areas, be that fuel storage areas, diesel generators, for example, on the gantries, we look to apply known principles within that guidance to address those areas in isolation to then form a sort of wider fire safety approach for the building. But looking at the sort of means of escape, the life safety aspects of design, sort of taken away from property protection for a moment, we often do find that these buildings have an incredibly low occupancy. Although a data center may have a significant footprint of tens of thousands of square meters, more often than not, the occupancy is far less than 100 occupants, and that is often split over shifts as well. These buildings operate on a 24/7 basis, but we typically see anywhere between 40 and 70 occupants on a permanent basis in these buildings. So, things like egress widths, etc., they aren't as crucial within data centers, but should still be considered nonetheless. But it often comes down to minimum requirements anyway. Travel distances can and often are the biggest challenge because of that footprint, and how we use guidance such as 9999 and the systems that we have in the building to present possible variations to the minimum requirements of the standard often enables a good and balanced approach that remains within the confines of the standard. So leaning into the systems there, how do we facilitate early warning of fire under typical guidance and under the regulatory position and under the say the guidance that it reinforces that regulatory position? These buildings would require category M alarm, but often that isn't deemed sufficient. We've seen it previously with particularly the fire service, where they don't deem a manual alarm to be the minimum requirement. Obviously, that moves to an automatic alarm if an A3 risk profile is adopted within the building. But typically, if it's A2 or A1, then category M would be acceptable, but really it isn't acceptable because of the number of systems that need to interface with the fire alarm throughout these buildings. In view of the operational requirements of data centers, they just don't work. There are a number of systems that, such as VESDA, for example, that is often a client requirement, a need because of high ceilings. It just wouldn't work through the adoption of a category M alarm. So providing a suitable sort of base alarm provision that further systems can tie into is an important consideration. Obviously, the opinion of the AHJs is incredibly important, and trying to sort of foresee that is an equally important objective. How do we demonstrate that a suitable level of alarm coverage has been provided? And just mentioned there, VESDA systems are required because of the volumetrically large areas. So interfacing and having a good base alarm system is incredibly important. Through so materials and construction, through application of guidance, we can look at a granular basis, view each individual component of that data center. As we looked through that internal sort of figure, or the figure of the internal arrangement of the data centers, they are almost quite cellular in the makeup. Risks are quite sort of broken down and constricted to the space in which they're located. So we break it down to look at those individual areas and view obviously the risks posed by those areas on an individual basis. How do we apply? How do we select? And propose materials that are suitable for those risks is incredibly important. Owing to the type of building data centers we often don't see any requirements in terms of, or any extensive requirements, should I say, as we do elsewhere, such as obviously the residential sector. We don't see the requirements for external surface spread of fire. The materials, there isn't a requirement to apply A2 or better construction to the external facade of these buildings. However, that can often be driven elsewhere by property protection requirements, or where external risks are deemed to be in close adjacency to the building. As we mentioned earlier, gantry provisions, generators, fuel storage, being in close proximity to that external facade can present and give good argument to select materials of a more onerous classification. The internal building linings, for example, we only typically rely back on the minimum requirements as a minimum, but we do see often the need to apply either FM approved or UL tested materials that are specifically tailored to data centers. For instance, FM provide guidance on hot aisle and cold aisle containment materials, the selection of particular types of plastics, etc. And having that cognizance to know that information is available helps you to tailor a fire strategy specifically in this regard, sort of away from the minimum requirements of the building regulations. The biggest challenge we often find is fire service access, as you can imagine, being a very large building, either having a full perimeter access to that building, more often than not requiring 100% perimeter access, is quite difficult. We do tend to see a site perimeter access route around them, but on existing sites or retrospective sites where either the building's been refurbished or it's undergoing a change of use to a data center, for example, from a warehouse to a data center, obviously that consideration of perimeter access was never a true consideration at the original design stage of that building. So having that perimeter access around the building can be often quite a challenge. So how do we look to overcome that? And we often try to present a multifaceted approach, in the sense that we have perimeter access as best that can be achieved. Often we try to push for modification to that access route to increase perimeter access, but at the same time, the provision of dry rising mains or wet rising mains to support the fire service to obviously enter the building, as opposed to fight the fire defensively, actively seek to fight that fire and give them confidence to do that, give them multiple directions of attack to facilitate that, and give them the provisions in order to do that is a very important consideration, particularly when we've got gantries, rooftop located plant, and as we're seeing more often now, multi-story data centers as well. Often that multi-story aspect, given the floor height, can start to push us over the thresholds of where perimeter access is no longer acceptable anyway, but still providing that perimeter access even in those conditions does enable this multifaceted approach to be developed. The balancing of water is always a incredibly difficult challenge as well. Many of the data center cooling systems rely on that water and often run to destruction. So how we maintain the cooling for building services which aren't undergoing fire conditions, whilst also delivering the required and necessary amount of water to the fire service to fight any possible fire on the site, is always a very balanced argument from all parties involving all mechanical engineers on these projects. How do we achieve each one of those objectives, and particularly the fire service and aligning to the 9990 requirements. Next slide, please, Jonas.
I believe this is where I'm taking over, Josh.
I believe it is. It is, yeah.
Okay.
You get a drink.
Just to add, just to add on the topic of the balancing of water requirements, it's more about ensuring that the water on site is distributed equally or as necessarily for the systems, for the fire safety systems as well as for the non-fire safety systems, and that is more surrounding the items like effectively making sure that the site is not wasting water and not using water unreasonably, because obviously with the necessary requirements for water supplies and planning permissions, there are limitations in existence for existing sites on how much water can be stored and retained by certain buildings. So with regards to typical challenges that we see when it comes to gantries, as Josh already mentioned, there are numerous installations on the gantries, such as diesel generators, electrical equipment, and chillers, all of which present fire load and ignition hazards. Gantries themselves, there are typically two major approaches when it comes to structural fire resistance design, and it also depends on the proximity between the gantry and the main data center building, and also other items that play a part in that design, such as if the structures are interconnected, such as if there are suppression systems involved on either side, either data hall or data center or the gantries. So the two main approaches are typically a non-rated structure or otherwise a R60 rated structure matching the rating of the building, which typically lands in that region. The external fire spread and finishes are also important. So typically, whilst these are structures on the same site, so it might not necessarily be an item that requires consideration from life safety perspective, but property protection does play a role in there, because an incident involving a gantry is something that is undesirable if it then spreads within the gantry or into the building or onto the building itself. So this is typically achieved through the selection of non-combustible or limited combustible materials for the building facade, as well as the gantry, as well as equipment enclosures. There's also, when it comes to any electrical equipment and selection of electrical equipment, there are some steps that can be taken to ensure higher resilience against fire. And that would be, for example, choice of high flash point mineral oils or suppression inside the generators themselves. Often when it comes to data centers within cities, there are requirements from the planning permission with regards to hiding the equipment and making the gantries more visually appealing. So again, selection of the materials to enclose the gantry is important to ensure that we're not introducing more combustible material to the site. And often planning requirements come with requirements for items such as green walls on the gantries themselves, and those are also a topic for fire safety themselves. The green walls themselves can contribute to the fire spread, but also the green walls, the construction of themselves can involve a large number of membranes and plastics, which then also at the time of drought can increase the overall fire load and undesirable condition for the site overall. With regards to the fire brigade access that Josh already mentioned on the previous slide, yeah, large DCs would typically require 100% perimeter access, and the gantries then restrict that access, so that the perimeter becomes the perimeter access strategy becomes effectively non-compliant with the approved guidance or with the BS 999. So access around the gantry and to the gantry needs to be considered, as well as egress from the gantry itself. So all of those play part in all the B1 to B5 requirements as well. The materials on site, the hazards that are present are diesel. There's also a lot of refrigerants and coolants that are involved in the in the mechanical cooling equipment. There are also battery rooms. The two prevailing technologies used are valve-regulated lead acid, VRLA, or lithium ion. Lithium ion seems to be on the rise, but we still see both technologies almost equally used. There's also an involvement of firefighter water runoff, and the water runoff needs to be considered for specifically lithium ion, as well as any potential diesel contamination. Then there are transformers and HV equipment and loading bays. So considerations for all these aspects and all these hazards, on projects, typically it's really good practice to ensure that there's an early liaison involved with the building control officer and fire rescue service, and ensuring that all parties around the table understand the site and what a data center really is, what are the contents, what are the hazards. There are also other regulations that come to play beside building regulations, such as COMA, Control of Major Hazards, DESIRE, which is explosive atmospheres. And the HSE has got some level of relevant applicable guidance available. In addition to that, again, NFPA is a resource that often provides a further level of detail when it comes to the design, development, and the standards available. So the control of major hazards, it may not necessarily apply depending on the size of the site, but the HSE guidance with regards to the safe design of diesel storage can and still apply and should be followed. Again, because some of these regulations are beyond what some fire engineers currently consult on. It's a strong recommendation that a process safety specialist is involved, who can furthermore assist with the COMA DESIRE assessments and necessary submissions to the relevant authorities. The firefighter water runoff is something that has not been particularly well designed in the past, and existing sites might not necessarily have the provisions. But now with the prevailing technology, for example, for lithium ion, where there are effectively chemical reactions that can produce toxic runoff, or runoff that is effectively required to be processed accordingly, specifically for sites that are in close proximity to water sources, it is important consideration that the firefighter water runoff is catered for through capture or effectively through on-site capture. And when it comes to VRLA battery rooms, VRLA technology produces hydrogen when it's charged. So it's important that hydrogen detection, ventilation, and other safety systems are put in there, such as intrinsically safe electrical equipment. So it certainly is one of the more complicated buildings around to be designing for. When it comes to property protection, the common stance in the UK for fire engineers has been life safety only. This approach does not quite work on data center projects, and property protection needs to be considered, and it needs to be aligned with the life safety. The existing UK design guidance is often insufficient when it comes to property protection, and the challenges also come about from the fact that the data centers are falling under the critical national infrastructure classification. So to counter that, often client and insurer requirements need to be considered, and they can come from multiple different areas. Often client own standards are prepared for data centers, and it's important to know whether they exist and have them available when working on these projects. When it comes to property protection suppression systems, they are often seen as less reliable or less stringent when it comes to the design, as opposed to life safety, due to often some of the standards requiring less redundancy, but they often require higher demand when it comes to water volume and the design densities. And overall, when it comes to property protection, one item that's quite often not necessarily well picked up in earlier design stages is the resilience and redundancy when it comes to power streams and separate pathways. So effectively, a data center is designed as a series of compartments that a failure in one should not impact the other ones. So typically when you see certain pathways, you will see that there are fire resistant construction separating separate cable paths serving, for example, data halls. Each data hall is typically its own fire compartment, and typically if you've got interior electrical rooms, again, high degree of compartmentation. If you've got exterior transformers and they're in close proximity, you will often encounter a firewall construction between the transformers. So to counter and prepare for any property protection requirements, ensure that you use appropriate guidance that's available from industry bodies such as LPC, FPA, NFPA, FM Global, EN series of standards, and CFPAE, and then obviously consult everyone on the project team, especially client representative as well as insurer representative. In terms of other considerations that need to be catered for, data halls often have a high background noise. Similar conditions arise in equipment rooms and gantries. There's often a lot of noise because the mechanical systems that are in those spaces that cool provide the cooling or the basic supplies to the building. There are often long travel distances in data halls, corridors, gantries, and roofs. There's a high volume of moving air in data halls, which impacts the detection systems. Sometimes it can impact other systems because you can have reasonably high volume of air being moved around. So it can impact your fire door opening forces. It can impact your system supports. Data centers require continuous operation. So if you have an incident in the data center, it's typical that there is no power isolation. They continue to run until either the incident is taken care of or until a big red button has been pushed somewhere because somebody has the authority to say so, or until the data center has failed. So it's something that needs to be considered. There is no automatic shutdown on fire detection, as you may see in other buildings. There are tall spaces where the data halls are often 6, 7, 8 meters tall, which impacts your equipment maintenance, your equipment positioning. Also, in turn, it introduces tall walls into the buildings, and often you will see systems using insulated wall panel systems, which then in turn impacts your material specifications, your maximum permissible heights, lengths, and obviously fire stopping as well, because insulated wall panels, they are a separate category under the EN requirements of fire stopping. You cannot assume that your concrete tested fire stop will perform in insulated wall panel, or that your plasterboard fire stop will perform in an insulated wall panel. They are entirely separate system categories. There's no cross-pollination right now with regards to the field of application. Furthermore, there are also novel technologies being brought into these buildings, such as photovoltaic panels, typically on the roofs, liquid cooling, as opposed to air cooling. There's also cogeneration being brought to these sites, where obviously there's a lot of waste heat that's available and that can be used for other areas, such as municipal heating, such as pool heating, or anything you can think about. There are also green roofs and green walls often deployed on these sites. The one item that also needs careful consideration is integration with security. The entire site is usually highly secure, have a secure perimeter, secure doors, and it's difficult to get to the site, and it's difficult to leave the site, and also needs to be considered with regards to door unlocking, fire alarm, signaling, etc. There's a big benefit to data centers, and Josh already mentioned that it's low occupancy space, and usually data halls and corridors generally present a low fire hazard spaces, where there is an extremely controlled environment, it's sterile environment, typically limited combustible load, and it's very highly managed spaces. So you don't necessarily see sites that would be unmanaged or poorly managed. And over to you, Josh.
Yep, thanks, Jonas. So obviously the last of the sections now, but what is the, why is it important to consider fire safety in data centers? Obviously, the biggest issue and the one we're always striving for is demonstrating that the building is safe from a life safety standpoint. Taking into account the different types of occupancies, layouts, what might be in the building, and how that might have an effect on the life safety of those occupants. Secondly, the reliability of the building systems. Can it continue to compute and support that data center requirement? And you look at that storage of the data in the event of a fire. Can it be easily recoverable after a fire? And can a fire be prevented from spreading to maintain that reliability? Because ultimately that leads into the last item there, which is cost. These buildings are incredibly expensive, hundreds of millions of pounds more often than not, from an upfront cost for the operator. But replacement of those internal building components is equally as costly. You have to buy it once, it's costly. If you have to buy it twice, it costs even more. But ensuring that that building as well, because of the expense of its contents, is incredibly high. So how do we propose systems which can potentially reduce that? So if we look more closely into the safety aspect, as mentioned, compliance with Part B of the building regs is always the foremost objective. Obviously, how we go about doing that through the application of the guidance, as mentioned previously, is always important. Measuring it and assessing it and presenting it within the bounds of known principles is always the best and most appropriate means to do so. How do we identify specific risks? You may have occupants who are working alone, for example. We, as we mentioned, we have generator gantries, plant gantries, should I say, is a wider statement, but you have generator gantries, plant gantries, UPS gantries, cooling gantries on the rooftops, often areas where occupants can be working alone, and linking into what Jonah said a minute ago, often noisy environments. How do we alert those occupants, and how do we provide them with a means of an adequate means of warning them of a fire within the building or within the local vicinity? How do we lean into, and how can we take benefit from the inherent building properties that are affected onto the building through the application of property protection requirements, client ERs, FM suite of documents, where often a more onerous level of fire performance within that building is required? How can we use that to our advantage to demonstrate a higher and more onerous level of life safety within the building? And how do we integrate the building systems within the building, which can often conflict with the operational systems of it? For instance, data centers, when it comes to cooling, don't shut down HU systems. They don't shut down any form of cooling arrangement. It continues to operate more often than not to destruction, which is in a direct contrast to the typical way of thinking. So how do we overcome that is always an important aspect. And how do we demonstrate it to the AHJs that what has been proposed is an acceptable arrangement, and also mitigatory measures off the back of that are suitable? So next slide, please, Jonas. So in terms of reliability, more often than not, right after life safety, the reliability is the next biggest item on the agenda of operators and clients. The data centers, in terms of uptime requirements, often the specifications refer to something called 5 nines, which is 99.999% uptime, which, as you may gather by that percentile, is quite a high level of reliability. I think if we could all guarantee that of our cars and other aspects of our everyday lives, we'd be quite happy with most things we buy. So having that in a building as complex as a data center and needing to achieve that is incredibly important, and how we demonstrate that risks relating to fire are suitably mitigated are obviously incredibly important to the operator. And what we often find is operators are very open to what we may put forward to demonstrate that, to give them that added level of comfort, so that if there is a fire, it's suitably contained within the building. It's not going to spread outside of the compartment of fire origin, or I say it's not going to. We don't like to think it will, but we try and restrict it as much as possible. As mentioned previously, it's critical. They are regarded as critical national infrastructure. So obviously having a a high level of reliability, both physically of the building systems and for supporting systems, is of paramount importance. And these buildings do form part of an ecosystem. It isn't often just one data center that provides that link between between the sort of ecosystem of data that we if we think of it as an ecosystem, it's from the operator of these data centers to us as users. There can often be multiple data centers involved in that chain. So failure of a single data center can end up putting more burden onto the other data centers within that framework, within that system. So reliably protecting against fire in that regard is also incredibly important, so as to not overload the network, so as to speak. Next slide, please, Jonas. Finally, cost. As I mentioned, they're incredibly expensive to build. Even from a shell and core perspective, they're incredibly expensive to build because of the size of the size and footprint of these buildings. So then, when we come to fitting those out with server racks, backup power systems, the UPS systems alone, as I mentioned, using novel technologies such as lithium ion, can present higher costs. So the risk of losing those items and then having to replace those items, not only from a physical cost perspective, but also reputational cost for the operator. I think I mentioned it previously in this presentation that more often than not, we have the data center has or is operated by an overall operator, but that is then tenanted out to tenants. Your sort of more familiar faces within the technology industry that we may you and I may know. These guys take those spaces out, and if they see or note that the fire safety provisions within the building aren't necessarily up to their specification, that can cause them to move elsewhere, away from that operator. So obviously having a fire within your building that isn't controlled, isn't contained, isn't suppressed, or isn't initially appropriately mitigated against, can serve negatively in terms of revenues for data center operators. Repair and replacement of those components, as mentioned, is incredibly costly from particularly a time perspective. You can imagine the systems that these servers have to integrate with. Takes time to set that up. It takes man hours to set that up. So the loss of those systems and the replacement post initial cost and replacement cost can continue to spiral and grow. Insurance premiums are always affected. We often see that through the provision of additional systems, although there may be an upfront cost to the operator, actually providing more onerous and robust systems to fight against fire and back up that property protection aspect of the design can result in lower and reduced premiums as part of that upfront cost to the operators. But equally, should a fire occur, that can then result in an increase to their insurance premium. So keeping that under a sort of under a microscope almost is an incredibly important consideration for operators, and they do try to see the sort of wider picture as opposed to sort of narrowing down to that initial cost of, say, us recommending an enhanced level of suppression, for example. Looking at the wider picture of reduced premiums over the long run. And lastly, the environmental cost. I think Jonas did mention it on his slide with regards to firefighting. Often chemicals, compounds, and other associated chemicals or products of combustion can make their way into the watercourse as a part of firefighting runoff. Fuels, for example, how do we appropriately provide fuel interceptors? Is the means to do that? It does present a risk to the natural environment as well as the actual physical cost of the building.
And in summary, so data center is not a warehouse. Competence is key. Identifying own limitations as well as limitations of others on the team is always important. It's important to understand the building and the hazards, knowing the requirements, statutory, client, and property protection. Repetition is key, and therefore data center is not a warehouse. and it should not be designed as one. Ensure you monitor the materials on site. Questions need to be asked about what different rooms contain, what different rooms do, identify the hazards and the mitigating measures for them. Obviously consult authorities in the early stages and at the key milestones. Ensure that other fire safety regulations or fire safety adjacent regulations are also considered through bringing the appropriate specialists to the team as well. Use the appropriate standards that are available out there. Don't be afraid to necessarily seek other guidance and information beyond the UK. And lastly, a position for life safety only is not appropriate. And I think we are towards the end of our presentation, so we should be open to questions. And there's also some other useful resources that you can go and search and view afterwards to understand data centers a little bit more.
Thank you both for the presentation. Really appreciate it. So we'll just, because we are almost like 6 p.m., we'll go through some questions very quickly. So I kindly request the also responses to be quite short, let's say. But in any case, you have on the presentation, there are the emails. You can always reach out to Jonas and Joshua through their emails. So may I start with Ben's question on the occupancy characteristics? Do you think the majority of occupants are sufficiently familiarized in order to have the A1 to A3 risk profiles? And also with regards to the maintenance, is it undertaken mainly by staff on site, or do they use normally outsourcing contractors? So this can be also this is also related to the risk profiles for occupancy.
Take this one if you don't mind, Josh.
Yeah.
So typically, site training is required for anyone coming to site, even if they are not part of the permanent staff. So as part of the site training, anyone will become familiar with the provisions on the building. Again, as a secure site, there's often requirements for vetting, and typically, if it's a contractor staff coming to site, then they will typically be retained for a period of time as well. So the familiarity assumption, I believe, rests and remains, and it's supported by the management provisions and the secure facilities that we have seen. I'm not aware of other, let's say, unfamiliar staff that would be typically coming to these sites. That's not a common practice.
Thank you, Jonas. On the next one, Aziz is asking with regards to the height classification of the gantry part of the building. Is it commonly observed that these structures consist of multiple levels connected by open stairs and are typically unoccupied? So the interpretation in such cases is that due to their non-occupancy, they are not required to have any fire protection to the stairs. Given this, could you please confirm how the height of these structures should be classified? Would it be 0 meters, reflecting the non-occupancy status, or should it be anything different?
Do you want me to answer that one,
Very good question. Yeah, go ahead.
Unless you had an answer already in the forefront of your mind.
I'm thinking, yeah, I'm working one up. Yeah.
Yeah. No. So typically we would look to apply the Annex F considerations of 999. It's effectively the plant spaces, and as is noted, they're effectively unoccupied structures. They are, as mentioned in the presentation, they are separate structures too. So obviously reducing or omitting in its entirety the protection to that structure is, we believe, within the confines of Annex F of 9999. Separately to that, there are also further considerations towards that decision in terms of how do we rate the structure, the stairs, etc. To that to those gantries. Obviously, if it's not got a period of structural fire protection, and you design it to Annex F, obviously your travel distances are inclusive of that unprotected stair to the foot of the stair from the most remote area. Often we find multiple stairs to these gantries, always at least two vertical means of escape provisions. often located at obviously opposing ends of that gantry, and they do tend to work quite well in that regard without the need to provide that protection. But at the same time, there are other considerations, fire service access. If the building is, the gantry is not provided with structural fire protection or a protected stair or any means of separation to that stair, then the attitude of the fire service may be not to actually actively mount a gantry and fight a fire actively, instead relying on that perimeter access provision. But we often find with the HJs as well that sitting on the side of the fence of no applied structural fire protection or separation to the stairs is an acceptable approach.
Thank you, Joshua. On the next one, have you ever proposed NFPA 13 sprinkler system obviously using the BS 9999 reduction from, let's say, A2 to A1 risk profile? And if yes, what was the response from the authority having jurisdiction?
Typically, we do not use reduction in risk profile using any system other than BSEN 12845 life safety. So the answer is no.
Great. Yeah. Have you ever encountered any issues with the high velocities of cooling air for the data racks impacting on the sprinkler head distribution, given that the data centers are required to run, as you mentioned also on your presentation, to failure, to destruction, and requiring, let's say, sufficient cooling to keep them at normal temperatures?
Yes, I mean, where you've got sprinkler heads installed in elevated temperatures, you choose appropriately elevated temperature sprinkler head, oftentimes about 93 centigrade rating. And with regards to the high air velocity, quick response sprinkler heads are typically selected. So that is on the back of FM global data sheets as well as NFPA, both of which I believe sit on have been effectively considering also both of these elements in data halls, specifically the FM global data sheets that have been also drafted specifically for data centers. So the increased temperature is addressed by increased temperature head, and the high air velocity is addressed by selecting quick response sprinklers.
Thank you, Jonas. On the next one, does the UK have any guidance for contaminated firefighting runoff water collection? If I may on this one, because it's generic one. Yes, there are like many different guidance. For example, you can find from Water UK, governmental environmental permits. I think thank you, Ben. He has already replied on this question as well with an environmental policy, the one from UK Fire and Rescue Service, and also one from the UK protocol for the disposal. So there are many you can find, and also maybe on the sector that you are working on, maybe you can find some in particular. But UK has a lot of different, many policies with regards to that. So I'll go to the next one. If the data center is located within the Greater London area, then London Plan 2021 and is applicable. Would the policy D5 for evacuation lifts be applicable in a situation where the floors above the ground are expected to be visited by clients, engineers, or visitors? If you have like any experience you have more experience on data centers, so do this building require inclusive design, including these evacuation lifts?
I'll be quite honest on that one. No, we haven't come across it, but at the same time, it will be considered obviously a major development given the overall footprint and size of the building. I think as well consideration for the layout of data centers. What we often find, as we noted on that figure previously, is the 90% of a data center effectively is unoccupied, except for maintenance access only. So if you were to apply policy D5 specifically, that may only necessarily be applicable to, say, the office areas or limited support areas. So, you know, I wouldn't sort of tar the whole building with it, but look to again break it down on those sort of constituent components. We have seen the comment raised by LFB elsewhere on the project, but that particular project did predate the London plan. So obviously that was dropped fairly hastily, but obviously it has been raised. So I imagine it's going to be a trend that we'll see more often going forward.
Specifically office areas, yeah, need to consider it.
Thank you, guys. Do you know if there are any FM approved gas suppression systems suitable for lithium-ion battery installations? For example, in FM DS533, there is a recommendation for sprinkler system.
That's right.
Yeah.
Currently under FM only water for lithium-ion. That's as far as I know. There may be, but from my awareness, it's only water.
Thank you, Jonas. Another question from James. On some of the projects that James is working on, probably in his team, they have a multi-story gantries with a footprint of more than 1,000 square meter, essentially a small building, let's say in itself. So they see vertically stacked generator units on them. How do you approach gantries of these types for structural protection? And as a second question, they have also sometimes more than 1,000 square meter plus floor plates of only diesel generators. Also, what's the approach on that for structural purposes?
I mean, the structural purposes, it really depends where the diesel is located and what the structural requirements are for, whether they're for life safety or property protection. If they're for life safety, it would probably be triggered for firefighting. If the gantry is reasonably accessible, then I would say you can certainly take a look at the available guidance and pursue non-rated structures if the height is not excessive and if it's not property protection driven. If it is property protection driven, at that point, typically you can consider standard design guidance for what would a similar size building require. So there is, I would say, no fast rule that can be applied, but there are a couple of the considerations that we covered in our presentation that can play a part in that decision-making process for both life safety and or property protection. And it's all about adjacency to the data hall or data centers, perimeter access, if the diesel is only in one tier or if it's both tiers. Sometimes you also have generators that are just on the gantry and a diesel has got a separate storage, which then is pumped through a network pipework into the generators, which can also simplify the design, because at that point you have removed that fuel load from the gantry. And generally, when it comes to the design for the fuel load, at that point it's the HSE guidance or NFPA guidance for diesel storage that comes in, but none of those talk about structural protection of gantries. That point is entirely, I would say, not well covered by any available design guidelines. You'll have to use first principles to come up with a solution that works for the applied design.
Thank you for this. Another one is we need your view on the evolving risk of decentralized UPS, where you have racks provided with a local UPS through in-rack lithium-ion battery packs.
Mm-hmm. That is a entirely proprietary system or series of proprietary systems, because they are typically provided by different manufacturers. Those systems should follow the available guidance of the NFPA 855 and UL 9548 testing hazardous mitigation analysis process, where the design team, the fire protection and the fire engineer will be able to identify from the test evidence from UL 954A if there is a credible hazard for fire to cascade from the unit of origin. And if it has that potential, at that point, there will need to be mitigating measures beyond those already implemented. That's the current, I would say, industry practice when it comes to use of distributed UPS systems. So there's a lot of evidence that's required in that process to establish the safety of those systems. And then obviously when they are used, it comes with a lot of other considerations, such as safe handling of those, such as when they're end of life, how are they disposed? Where are they stored when they're new? Where are they stored when they've been dropped, for example? And so, yeah, NFPA 855, UL 954A, and the EN requirements are coming in as well, so which will likely be similar to that as well.
Thank you, Jonas. And last, before we end this meeting, it's more like a note, let's say, with regards to the information and wayfinding, which is to me also is very important, because we are talking about the firefighters as well when they have to tackle a fire in such a building from the outside. Normally it's like a warehouse, although you mentioned that obviously it is not a warehouse with regards to the fire safety design, and the expectation for firefighters may be a large, let's say, undivided compartment. So it's very important to mention that the interior layout and systems, long travel distances, hose distances, all of them present very important hazards for the firefighters tackling in any incident, and for which firefighters may not be prepared for. We need to have this in mind as well. I don't know if you have any view on that. So
to our building operator projects and clients, we always recommend a robust emergency response plan to be prepared for that, including emergency, fire emergency file, and most importantly, site familiarization visits. And all of those items are also required under the FM Global data sheets. We've mentioned FM quite often. They have a publicly available suite of documents guiding properties that fall under their insurance scheme. Other insurers will have similar type requirements, maybe not as well developed as FM Global. But anyways, familiarization visits, cool. Fire emergency file, and emergency response plan. All of those are part of the equation to ensure that the first responders are well prepared for the building.
Thank you. I think that was sorry, Joshua, go ahead.
Yeah, no, just to patch into that though, Jonas, as well. Obviously, consideration of a fire control center. It's a complex building. We typically do recommend them for there's that many systems within data centers in terms of overrides for air handling units, cooling systems, etc. Even post fire smoke clearance, having a single centralized location for the fire service to act as a bridgehead is a fundamental consideration. So would make that recommendation as a minimum for those interested.
Thank you for your input. Guys, I think this is the end for today's webinar. I would like to thank you again for your presentation and your time for this webinar of SFP UK chapter. And also I would like to thank all the attendees for this one. I hope you enjoyed, and it was finally informative and useful. Thank you, guys. Thank you, Joshua, Jonas.
Thank you. Thank you all.
Thank you very much.
Have a great afternoon.
See you all in our next webinar or any in-person seminar SFP UK chapter will be organizing. Thank you, and goodbye all.
Thank you.
Thank you.
Bye-bye.